In this section, we will discuss how to find confidence intervals for a population where the standard deviation is known. So we begin with a confidence interval. A confidence interval gives a range of values that is likely to contain the true value being estimated. Now, our next definition is confidence level. The confidence level is a percentage between 0 and 100% that measures the success rate of the method used to construct the confidence interval. So here in this somewhat grainy photograph, we see a normal distribution curve listed. And then what's highlighted here is the middle portion is 90% of the entire area under the curve. In fact, it's the middle 90%. So since this is the middle 90% and we know the entire curve and all is 100%, we see the portion to the left that's not included plus the portion to the right that's not included must together add up to be the remaining 10%, and that's equally distributed because the normal curve is symmetric. So these two remaining pieces have 5% of all the data value. Now instead, what if we talked about instead of 90%, we were instead interested in 95%? Well, we would want the original middle 90% from before, but then we'd also want to add on an additional 5% in both directions. This shaded section represents 95% of the area under the curve. The two tails, both the left-sided tail and the right-sided tail, then account from the remaining 5% split equally in two pieces as 2.5% left over on each side. So whenever we talk about levels like 90% confidence level, 70%, what you should visualize is our normal distribution, and whatever that percentage number is, we're wanting to find that middle percentage, and that's our area under the curve. So in this case, 95% confidence means we have the middle 95% of the curve. Now we know that percent of the area under the curve could be translated to the idea of area under the curve. And we know area under the curve could be then understood from our area and z-score chart. So to get any area under the curve, we could use this chart to find the area and then get the corresponding z-score. And that's exactly what was done here. So as you can see here below, the z-score that corresponds to containing the middle 95% is negative 1.960 up to 1.960. And in our upcoming example, we're going to see exactly how we could find the z-score that corresponds to a certain confidence level. So in this next example, we're asked what z-score corresponds to a 90% confidence interval. As we're first getting used to this, I would encourage you to quickly draw a normal curve just to help you focus on what's going on. So let's draw that. And we know we want the middle 90%, so I'm just sketching that I've got 90% of the area enclosed in this section. Now we know 90% out of 100 leaves 10% left over that has to be split in half. So the remaining 10% gets split in two, so each of the tails is 5%. So 5% off to the right and 5% off to the left. Now, one other thing that we haven't highlighted maybe super frequently, but it's an important fact about normal distribution, is that they're symmetric. So the z-score, we know that corresponds to the middle height here, is 0. But then if this is the first 5% and this is the last 5%, then the z-scores are the same absolute value. It's just the one to the left will be negative, and then the one to the right will be the positive version. And we'll see that soon with our chart. The way we can bring the chart into play is we need to translate these percentages into how much area is taken up in terms of a decimal. So we need to first turn the percentage to a decimal. So to change a percent to a decimal, you move the decimal place over twice, so 0.05. And since this is area to the left of the z-score we're interested in, we could see what z-score gives us an area to the left of 0.05. Let's go to the chart now. So here we're looking in the chart in the middle for an area of, if we write it down from before, 0.05. And as we look through these, I think the closest values that we can glance are this value and this one. And normally we say pick the closest, but in this case, if you'll notice, both are 0.0005 apart. So they're equal distance apart. I can't pick a closest. In this case, we can just average the two positions because it's halfway in between since they're both 5 away. So this one corresponds to negative 1.64. We're between negative 1.64 and negative 1.65. I know if I add these two and divide by 2, that's averaging it, I'll get exactly in the middle. And we'd get the z-score of negative 1.645. And often for our purposes, we'll then round the z-score to 2 decimal place, but this is the exact location. So here we will write that in. This first 5% of the area corresponds to a z-score of negative 645. Now with practice, we're going to know that the other z-score is the mirror image, but in the positive version. So I could write down immediately that this is 1645, but let's also verify that in the chart to make sense of this. If I'm looking at the area to the left of this z-score, do you agree at first I'm grabbing the middle 90% plus the first 5%? So what percentage of the total area is to the left of this z-score? Well, 5% from the first portion plus 90% from the middle, so that's taking up 95% of the total area. And we know if we have 95% of the area, that's a move the decimal place over twice. We should be looking for what z-score gives me an area of 0.095, and we're going to verify that indeed it would be 1.645. So we're just verifying this mirror image idea. So we look through our chart. We're looking for 0.95. And I believe our two closest values are again here and here. They're all 0.0005 apart, so there's not one that's closer. I'm going to average the two. The first one comes from 1.64. When we average the location, we get 1.645. And just to clarify, why are we averaging it? It's because both of these are the same distance apart. I can't pick a closer value. So in the case that you find two z-scores equal distant from the point you're interested in, you just average it to get the exact value you're looking for. So if this, we have verified that the z-scores that correspond to a 90% confidence interval is we would have the negative z-score, negative 1.645 starting, up to the positive z-score of 1.645. Our next example is the same idea that we just saw, but instead of a 90% confidence interval, they ask what z-scores would correspond to a 99.8% confidence interval. To help us visualize this, we start with our normal curve. Now you've seen an example like this. Start drawing your normal curve to show the middle 99.8%. And ask yourself what percent then is left to the two tails before and after. So we have this middle 99.8%. We know there's 100% in all minus 99.8% leaves us with 0.2%. Now that 0.2% is split to the portion that's before equally and the portion that's after. So we divide that by 2. And we see that we get a 0.1% before and after. Now the percents are important, but we can't use the percents immediately. We need to change the percents to their decimal forms to get the area enclosed in that region, so that from the area enclosed in that region, we can go to the chart and find the corresponding z-score. So remember, the key idea here is you get the percentages, but then you turn the percent into the part out of the whole. So let's turn that into a decimal. We move the decimal place 2 places to the left, and we get 0.001 is the area after. Similarly, 0.001 is the area before. And this is the value I'm going to look for in the chart to find the corresponding z-score. So we're looking for 0.001. These are 3 zeros, so that's too much. We'll keep going. And we see the area in question corresponds to a z-score of negative 3.8. And we know by symmetry of the normal curve, if the bottom 0.1% corresponded to a z-score of negative 3.8, then the top 0.1% would correspond to a z-score of positive 3.8. And again, we could verify that. Think how much area is to the left of this z-score altogether. to the left of this z-score would be 99.9%, or that would give us an area of 0.999. Let's look for that in the area chart and see if we don't get the z-score of 3.8. And I apologize here, I was saying 3.8, but as you can see from the chart, it's 3.08. So let's make that correction first. 3.08. Copying error there. And as expected, through symmetry of the normal distribution, we see at the z-score 3.08, we have an area of 0.999 to the left. So we've now found the z-scores that correspond to that confidence level. Now keep in mind, if you're given a different confidence level, for instance, what about 92%, 94%, you can always go through the process that we just highlighted in the previous two examples. However, since it follows the same pattern for the same normal curve, you will always end up that a 90% confidence level corresponds to this z-score that we found before. It's never going to change. Similarly, if you go through the process, and I would encourage you to practice on your own and verify these as a quick check right now, pause the video if you need to. 95% confidence level corresponds to a 1.96 z-score. A 98% confidence level corresponds to a 2.326 z-score. A 99% confidence level corresponds to a 2.576 z-score. And then you'll notice I left a few more blank. These will be for you if you'd like to write in different confidence levels corresponding to their z-score. Then you can have some known that you can reference as you do your homework problems. So before we go forward, let's translate this one, the 98% confidence level, into a drawing of the normal curve, just to practice understanding what's being expressed here. So here I've got a quick sketch of my normal distribution. I know if I have the middle 98% taken up here, what percent remains to be equally distributed in the left and right tail? Well, we've got 1% for the left tail, 1% for the right tail. Now think to yourself, where does this z-score come into play? 2.326 is telling you the distance away from 0 that you'd go in each direction. So in the positive direction, this is the z-score 2.326 away from 0, which is at the peak. But at the negative direction, this is a negative 2.326. And these are our two z-scores that in between them bound the middle 98% of the normal distribution curve. Now next I have the steps outlined to constructing a confidence interval. Specifically keep in mind these instructions are when the standard deviation is known. In an upcoming lesson, we're going to talk about constructing the confidence interval when the standard deviation is not known. So realize there's a different process whether the standard deviation is known or not known. Step 1 says identify the sample mean, our x bar. Step 2, find what we call the standard error using the formula sigma, our standard deviation, divided by the square root of n, where n is the number of items in the sample. So we just write down that reminder if needed. Step 3, find the margin of error. Now the margin of error formula is what's called the critical value times what we just found the standard error. Now what is this critical value? The critical value is the z-score attributed to the confidence level. The critical value might also be expressed symbolically as this z subscript alpha over 2. Then once we've done that, step 4 tells us the confidence interval is the sample mean minus the margin of error you just found, inequality symbol, our mu symbol for our population mean, inequality symbol, sample mean plus the margin of error. And if I wanted to express what the margin of error is in terms of this verbal description in mathematical symbols, that's what you see written here below. Now there is an important rounding note. Be sure you take note of this. If you've been given an x bar, a sample mean, then round your final results to the same number of decimal places that x bar had to begin with. So keep these steps, this page of your notes, handy as we go through the next examples. So in this next example, it says a sample size of 50 is drawn for a population whose standard deviation, this is key, the standard deviation is known here, so I can use the list of steps above. Find the margin of error for a 90% confidence interval of mu. Now, let's just look from above and copy down what is the verbal description of the margin of error. The margin of error is the critical value that corresponds to the confidence level we're looking at times the standard error. So as I'm working to solve this problem, I'm just writing down the formulas first. Writing down the formulas helps me figure out what I need to find, and it's kind of outlining the steps for me. So the margin of error is equal to the critical value times the standard error. Now specifically, it's the critical value for a 90% confidence level. And while I could go through the process that we did at the very beginning of the video to find that exact value, I could also, since this is a well-known confidence level, revisit my table and see that for a 90% confidence level, my z-score is 1.645. So if you're dealing with a nice known confidence level, see if you know it from the chart. If not, we've done a few examples of how you could find the critical value or the z-score attached to that confidence level. So this is equal to 1.645 times, now the standard error, that as a formula, if you look above in this page of notes, is the standard deviation divided by the square root of the sample size. I guess here I should write the square root of n so it's generic, and then we'll apply it here. So that will be our standard deviation of 26 divided by the square root of 50. And here we get, it rounds to about 6.049 for my margin of error. So if you're asked to find the margin of error, first write down the formula for margin of error. Realize that it multiplies two values. The first value is the critical value that corresponds to your confidence level, which you might need to find or you might have referenced in our nice table, times the standard error, and the standard error is the standard deviation divided by the square root of the number of individuals sampled. Now it tells us if the sample mean is 62, so here from this phrasing, we will want to write on our scratch piece of paper, they're telling us x bar is 62. Construct a confidence interval for the mean population mu. Now I've zoomed out so that we can see our formula here. It tells me the confidence interval is always x bar minus the margin of error. So I could say my x bar is 62 minus my margin of error 6.049 is less than mu, is less than 62, my x bar again, plus now the margin of error. Now I'll type both of these into my calculator and get my simplified value. For the first one we get 55.951. For the next value we get 68.049. And this will be our 90% confidence interval. Now part C of this problem says if the sample size were instead 40, would the margin of error, so remember our margin of error references what we did in part A, be larger or smaller? Now I'm going to talk about at the end how you could understand this just from thinking about how mathematical formulas work, but I'm going to begin with maybe an easier way to solve the problem. They're giving you a new value of n and asking is the margin of error smaller or larger. So you could just recalculate it and then compare the two. You don't have to understand how the formula works to see if I change this, what would change as a result. You could just do the calculation and compare. So now my new margin of error is equal to the same critical value from before, because that's unchanged, times the same standard deviation from before divided by the new value of n, square root of 40. Now we'll calculate this, and we get about 6.763. So comparing the two, this was the original, this is the new one if n is 40, and you see if n changes to be 40, it would indeed be larger. So that's the way you could always solve this problem. If they ask you if I change this, what would have happened? Do the calculation if you changed it and then compare. Now if we want to just think through this, we could still solve the problem without calculating it by turning this into a 40 here, do you agree that's a smaller number than denominator? Square root of a smaller number is a smaller number. You're making the denominator smaller, but in a fraction, when you make the denominator smaller, you actually make the overall fraction larger. So you end up with larger number times the original, which is what makes the overall margin of error larger. So keep in mind, if you end up making the denominator smaller, that makes the fraction as a whole larger, which is what created a larger margin of error whenever we decrease the sample size. So that's two methods to solve the problem. Go with whichever method makes the most sense to you. So we can make the margin of error smaller if we are willing to reduce our level of confidence. So maybe instead of a 95% confidence level, a 90%. We could also, though, reduce the margin of error by increasing the sample size. Now we could actually find what sample size is needed for a given confidence level if you know the standard deviation and the given margin of error. And that's what we see here in our formula. Now just to make it clear, this margin of error that we know we're okay with is depicted here by our m in the formula. So the sample size needed is equal to the critical value that corresponds to the confidence level multiplied by the standard deviation, all divided by the given margin of error. Finally, don't forget this last part, square the final value. Now we have this important rounding note. Whenever we're calculating this value of n, if the formula does not end up giving you a whole number, then round it up to the nearest whole number. Now, this key phrase is round it up. No matter what it is, go up to the next integer if it's not already an integer. And keep in mind that this might be violating your normal rounding rules, because in this case it takes precedent that we want to make sure we really have that minimum sample size and we're not underestimating the sample size in question. So for our next example, it says a population has a given standard deviation of 9.2. How large of a sample must be drawn? Now this phrase of how large of a sample, that's our n. We don't know what it is, but it's asking us to find it. Must be drawn so that we have a confidence level of 92%. For our population mean, we'll have a margin of error equal to 0.8. Now the only thing missing here is this 92% confidence interval does not directly give me the critical value. I have to first go back and figure out what z-score corresponds to that. Just for time's sake, I look back at the chart and 92% is not one of the ones that I was already given. I'm going to include it once we find it here so I can reference it again, but we will have to go through this process that we did at the beginning of the notes in order to find the z-score that corresponds to the 92% confidence level. So off to the side, we sketch a quick sketch of our normal distribution. We know we want to contain 92% in the middle of the curve. So think, what is that left over? If we've included 92% out of 100, there's 8% remaining. The 8% has to be equally split before and after. So that gives us 4% before, 4% after. Now we know before we use the chart, you've got to translate this percentage that's before, this 4% before, into an actual area value. So how would you do that? Write that on your paper. This corresponds to an area of, well, you move the decimal place 2 places, 0.04. So in the chart, I'm going to look for what area is 0.04, and then find the corresponding z-score. Once I know the negative z-score, I know the positive z-score is symmetric to that. So let's take a moment and look in the chart. Where do we find an area closest to 0.04? And as we look, I believe the closest we'll get here is in the negative 1.7 row with the 0.05 column, so that's negative 1.75. So we know for our critical value that's negative 1.75, and then by symmetry, this is exactly equidistant from 0, positive 1.75. And for our critical value, we're going to choose the positive version there. So then using the formula, we see the sample size we need is equal to my critical value of 1.75 times my standard deviation of 9.2 divided by my margin of error 0.8, all squared in my calculator. And when we type that into the calculator, we get this value. Now we know our rounding rule says it doesn't matter what the decimal is. If it's not already an integer, you've got to round up to the next integer, or the next whole number. So it's not currently an integer. So instead of 405, even though it's closest to 405, I must round up to 406. And just to make sure the point is clear, it's not 406 because of the rounding rules. In fact, normal rounding rules would say keep it at 405. But for this particular problem, we've got this rounding note that if you're given a decimal, no matter how close it is to the other value, you must always round up to the next integer. So we would need a sample of 406 for that level of confidence, for that standard deviation, and for that margin of error. Now reading through the next question, it says, if the required margin of error were 1.4, would the necessary sample size be larger or smaller? Now think through this problem. What's changed and what are they asking us to compare? What's changed is they've given us a new margin of error. Now the new margin of error would make the denominator larger. And if you make the bottom of the fraction larger, a bigger number in the bottom of the fraction makes the fraction smaller. So the overall number's smaller. When you square it, it still is smaller compared to the larger value that began with. So we could say that we know this would be smaller if we kind of understand how the formula works in terms of what happens when you change a portion of the fraction. But all of that kind of abstract reasoning is unnecessary. We could just recalculate it with the new margin of error and then compare the two values. So our recalculate should be about our same confidence level and critical value of 1.75 times the same standard deviation that hasn't changed over the new margin of error, all squared. And we get rounded, because we have to round up, 133. So we see our initial expectation that it would be smaller has been shown to be correct. So in these type of problems where it says if this changes, what happens as a result, remember you can think about it with just abstract reasoning based on how the formula would have to work, or you could recalculate and compare and get your answer. Now in this example, we've got a few steps. Let's read our beginning part. It says a simple random sample of 150 households. As I read through, I'm going to extract that information. That's my sample size. N is 150. Really quick, let's correct a typo here. Sorry for this. This says can. It should say mean. The sample mean number of personal computers is 1.32. So that's my X bar is sample mean. Assume the population standard deviation. Now, here it's the population standard deviation, not the sample standard deviation. So I'm going to use my sigma for population is 0.41. Construct a 95% confidence interval for the mean number of personal computers. Okay, what do you do for the confidence interval? Remember, you take the sample mean, 1.32, minus the margin of error between the mean and the sample mean plus the margin of error. Now, I have the sample mean. We already know the sample mean is 1.32, so that doesn't have to be calculated. But I don't know the margin of error. And to begin with, I need to ask myself, do I even know what the margin of error formula is? If I don't, I need to go back in my notes and write that down. How can we find something if we don't know what it is? So let's write down what that formula would be. The margin of error is the critical value times the standard error. Now, the critical value is based off of the confidence level we're interested in, so a 95% confidence level. We've done multiple examples where given the confidence level, we find the corresponding z-score manually. However, this 95%, if I'm paying attention, was already listed in our chart of known confidence levels and z-scores. So to save myself time, I could just recopy that. Okay, the critical value for 95% is 1.96. times the standard error. Now the formula for standard error is the standard deviation divided by the square root of the sample size. So in our case, that's 0.41 divided by the square root of 150. Now that will give me my margin of error. And now we come to our final calculation of the margin of error. And what I need to keep in mind here is when constructing the confidence interval, it told me in my rounding note that it all depends on if I'm given x bar, the number of decimal places there. Since there's 2 decimal places in x bar, I need to round this to 2 decimal places. So that will round to 0.07 is my margin of error. So then the confidence level is the sample size minus the margin of error. So the mean value is between that and the sample size plus the margin of error. Now both of these can be simplified. 1.32 minus 0.007 is 1.25. Population mean is between 1.25 and 1.32 plus 0.007. Oops, sorry about that. Is 1.39. So that is my 95% confidence interval for the population mean. So our next question says, based on this confidence interval from part A, which we just found, is it likely the mean number of personal computers is greater than 1.25? Well, our 95% confidence interval said the population mean is between 1.25 and 1.39, so we would definitely agree that yes, it is greater than that because that's our lower end estimate. Now our next question says, if the sample size had been 100 instead of 150, so it's saying pretend things were different, would the margin of error then be larger or smaller? Now we've seen these questions before. Well, you know, at this point you could either think about it and figure out what it would be, or you could do a recalculation and compare the two. Okay, now let's just think through it together. If this 150 had been 100 instead, that makes the denominator smaller. Now when you make the denominator smaller, you actually make the overall fraction larger. So this would have become a larger number times this, which would have given me a larger number as a result. So I can intuit that it would have to be larger if I shrunk the sample size. And if I'm unsure about that type of reasoning, then I'm just going to recalculate off to the side and verify for myself. The same critical value as before times the same standard deviation divided by my new square root of the sample size. That would give me, rounded to 2 decimal places, 0.08, which we see is definitely, as expected, a larger margin of error. Okay. Now our next question, if the confidence level were 98% rather than 95%, would the margin of error be larger or smaller? Now in this case, things have kind of reset. We still have the same sample size of 150. The only thing that's changed is the confidence level. Now looking at this formula, can you visualize if the confidence level changes to 98%, what part of this is changed? The confidence level corresponds to the critical value. Okay, so we would get a new critical value if we had a new confidence level. Now we know how to find the critical value, but we want to see if we can save ourselves time. So we go back to our list of critical values and z-scores, and we see we actually have it for 98%. That's a 2.326, so I'm going to record that there. So if it was 2.326, everything else left the same. Well, even before I type this into the calculator, we can figure out what's going on. This is the same in both cases. So you have same thing times, and look at the comparison. Now this is a bigger number when compared to the original. Same thing times bigger thing will give you a bigger result. We know that this is going to be larger as well. But we could carry through the calculation and see that as well. We see it would round to 0.008, and it would indeed be a larger margin of error. Okay. So as you complete this section of notes, remember these notes are always available for you. Exactly what you see me going through on the screen is what you have available in our course note packets that you can find in our online course. I would encourage you to print these out and make sure you take notes of our different formulas, and as you find different z-scores for the different confidence intervals, you can add that to your table of values so that you would have a nice repository. If you see a problem that says 92% confidence level, you already have the z-score found. So as always, if you have questions, feel free to contact me. I'll be happy to help you.